Good morning, everyone. So let's start this morning session of the second day of the Seventh Amazonian Symposium in Physics. And it's my pleasure to welcome today Professor Gonzalo Olmo from the University of Valencia. Gonzalo has been a long-time collaborator here of the graduate program in Belém, UFPA. He's a well-known researcher in many fields, in strong gravity, modified gravity, and it's a pleasure to see you here, Gonzalo. Although not in person, that would be better, but next time, hopefully. And so Gonzalo is going to be telling us about platypus stars, which is an intriguing name. Yet another black hole. So please, Gonzalo, go ahead and thank you for your talk.
Thank you so much, Carlos, for the introduction. Thank you, Luis, for the invitation to participate in this workshop, and everyone for being here. I wish I could be in the auditorium for the meeting, but this year hasn't been possible. I'm teaching a lot. But anyway, I'm going to, hopefully next time I will be able to join you in person. And let me start. Because I want to present a work that is not my original idea. So I must give the credit to these two students who are in the audience online, Caio Cesar and Nicolas. They came up with this interesting idea of a new type of star, and they invited me to give my opinion to them. And so I really fell in love with this with this kind of new object, and then we have been working together since then on this. And we are just finishing. This is still work in progress, but we are about to finish the first draft of this with these results. So so the motivations for this talk are simple. For this the study of new kind of stars is, as you know, that black holes are the natural candidates to explain observations associated to compact objects, like the collisions of binary emitters of gravitational waves, and also to interpret correctly the radio waves that come from the accretion disks of objects, very massive objects at the center of galaxies. But as you know, there are some limitations. The theories that describe the black holes is incomplete, in the sense that black holes, at least the black holes of their relativity, have singularities and have pose difficulties to combine quantum gravity with gravitation. And so there has been a lot of interest in the community over the many years to find alternatives to black holes, probably very compact astrophysical objects without horizons in particular, though non-singular black holes are well known. And there are also proposals like the Gravastar idea that represents a kind of exotic star with the Sitter core that in principle could mimic or reproduce some of the or represent of the observations that can only be justified in terms of black holes or very massive compact objects. But they have their own proper characteristics, so they are distinguishable from black holes, from the phenomenology. And particular gamma stars are, since they represent a kind of compact object without horizon, and the de Sitter core is typically interpreted as a manifestation of some kind of vacuum, quantum vacuum energy. Okay, then, but this vacuum energy has an energy density and a negative pressure, as you all know. So a natural question, and very simplistic question, related to this interpretation of the Sitter cores as vacuum energy, is to think that if really the cosmological constant really represents, or is really representative of the idea of vacuum energy. So, and then naively one can think that maybe vacuum is really empty. Okay, so, and this is what motivates, this simple question is what motivates this new compact object that we call the Platypus. Okay, so what I'm going to do is to describe the internal geometry that is built in terms of fluids. I will describe how these fluids appear and their properties, and then the continuity conditions, the pressure profiles, the compactness of these objects. And once we have the star built, completely built, then I will discuss a little bit about the phenomenology. So the talk is going to be very technical. Okay, I'm going to focus on calculations, very simple calculations, in fact, but to show you the basic steps to build one of these stars, these solutions, and we will briefly compare them with other kinds of stars, including gravastars. Okay, and why the name? Okay, why the Platypus? Because this, well, it didn't coin this name. It was the original authors, Caio and Nick, who proposed this name. And I really agree with them that a platypus is a kind of animal that if I tell you that something like this exists in nature, you wouldn't believe it, okay? So probably the same happens with this new kind of stars I'm going to show you. They are made out of pieces of different space-times. It's not exactly cut and paste, but smoothly joining different pieces in such a way that you can build one of these stars, okay? So, as I said, I'm going to focus on initially on the TOV equations, and then we'll derive a constant density star solution. It's an illustration because this is the key to build everything, our platypus star. And we'll also comment on gravastars, some very simple aspects of gravastars that make them, to distinguish them from these platypus stars, okay? Tomorrow, Luciano Rezzola is going to give a very interesting talk about, possibly about gravastars. I don't know exactly what he's going to tell, but don't miss that talk because it will be very interesting. Okay, so let me get into the details. And just to frame you, the mathematical framework is general relativity. Okay, we just have the usual equations of general relativity with a perfect fluid and a spherical symmetric static line element. So what I'm going to show you now are the equations that describe the stellar structure of these kind of fluid configurations, static and spherically symmetric, using this sense. Okay, these are the two equations that follow from Einstein's equations, and this is the one that comes from the conservation of energy and momentum. So this is called the TOV equation, the Tolman-Oppenheimer-Volkoff equation. This function that appears here, this A, is reparametrized in terms of the mass function in the usual way. So the mass appears here, this function. So this mass is like the Newtonian mass, okay? Because to get this quantity, this function, we just integrate the right-hand side, and this is just the usual Newtonian mass, but it's the mass that appears here, okay? Okay, so from these equations, in fact, manipulating this one, we can write it in this form, okay? And formally, it can be integrated if we give some equation of a state that represents the density as a function of the pressure. So we should be able to get this formal expression. Okay, this is very useful because now if we take, for instance, a constant density, we can integrate this equation and proceed. Okay, so this will help us obtain the constant density solutions of general relativity. Okay, this is well known. This is even in the book by Walt on gravitation, general relativity. You can find that solution there. But since it's very simple to derive, so I'm just showing it. So from this expression and putting the density constant, we get this result here. And this is a constant of integration, right, that we set by evaluating this function on the surface of the star. Okay, we assume that the surface is the region where the pressure goes to 0, P is 0, and the geometry outside the star is the Schwarzschild solution. Okay, this is why this motivates this choice of ansatz, okay? And this A dot, this is simply denoting the mass of the total mass of the star at the surface of the star, okay? This is the radius of the star, and that's it, okay? So from this expression, now we can isolate the function rho plus p and put it back here, okay? And in that way, with simple manipulations, we can write an equation for the function phi and solve it, okay, analytically. In fact, just simply note that in the denominator we get one a that comes from here and another a square root of a, so that it gives 3/2. And since the function a inside the constant density region is cubic in R, then the ratio R over R is quadratic, okay? And then this R that appears here can be written in terms of the derivative of A, so this can be integrated analytically, it's very simple, okay? And we get this final result, this quantity here, okay? Up to an integration constant. And then we must fix this integration constant in some way. In particular, yes, evaluating this at this expression at the surface of the star, okay, and imposing that a phi at the surface is just 1. Okay, so phi at the surface is 0. It's just a normalization. Okay, so we get this this expression here, and then we can use it back in the density, in the pressure profile, to obtain this expression for the pressure. Okay, this is the pressure for a constant density star that outside has the Schwarzschild solution. Okay, so this is very well known. And now, what those of you that are not familiar with this solution, what you need to pay attention is to the fact that the pressure has this denominator, and this is the difference of two positive quantities. So at some point, this could become 0, and then the pressure could go to infinity. Okay, so in particular, if you evaluate this quantity at R equal to 0, which is the center of the star, obviously a natural condition to impose is that the pressure be different from infinity. It does not diverge. So the star, to make sense, should have a finite density pressure because the density is constant. Okay, and then this condition from here, it follows that 3a sun 1/2 minus a 1/2 at the center, and this is 1. This should be bigger than 0. Okay, and in the limit, when this is 0, then we have this. And from this expression, using this quantity, we obtain an expression for the mass radius relation, which is this function. This quantity is called the compactness. Okay, so this m over r of a constant density star can be at most 4/9. Okay, which is smaller than the compactness of a Schwarzschild black hole. Okay, you know that from this expression for a Schwarzschild black hole at the event horizon, this quantity would be 1/2. Okay, but this is 0.5, and this is 4/9. This is smaller than 1/2. Yeah, it's smaller because the highest compactness is the one of the black hole. Okay, so this means that you cannot put an arbitrary amount of mass inside a given radius with constant density. Okay, so there is a natural limit for stellar objects in general relativity that is derived analytically with this simple model. But this conclusion, this limit of the compactness that should be smaller than 4/9, can be generalized to arbitrary stars as long as the density profile is a monotonical function. Okay, because you can describe any density profile in terms of a sequence of constant density stars. Okay, so we have this limit. So we cannot explain extremely compact objects in terms of constant density stars, because observations indicate that there are objects which are more compact. Okay, and this is the solution for a spherical symmetric static star with constant density in general relativity. Okay, this is one of the elements we will use in a while to construct our platypus stars. Okay, and now let me mention a slide briefly what a gravastar is, or what is the pressure profile of a gravastar. So the gravastar is an idealized star, is an alternative to a black hole without an event horizon, but that at the center has is dominated by vacuum energy. So it's like an equation of a state here in this region that is approximately 0. Okay, for a cosmological constant, it would be exactly 0. It's only just at this limit where the cosmological constant equation of a state is really satisfied, but there must be some modification, some departure from that idealization in such a way that at some radius we can attach a fluid, a sphere. Okay, this is like a thick shell or a crust, an external crust that is supported by the negative pressure of the vacuum energy inside. Okay, and then so you have an internal mechanism that is this vacuum energy that supports an external layer of fluid, and then this is the fluid, and here outside, when the pressure goes to 0, is where we have the Schwarzschild solution again. Okay, so this is how the pressure profile should work in a gravastar. Okay, since in the internal region the pressure is approximately minus the density, and so it must be negative. Okay, this is the 0 pressure. Okay, so this region is negative, and then the pressure profile crosses 0, grows to a maximum, and from that maximum outwards we have some regular fluid. Okay, so the point is that with the equations that I showed before for this compact constant density star, or simply for perfect fluid isotropic fluids configurations, one cannot build a gravastar. And the reason is simple, because if you look at, for instance, at this point where there is a transient from negative pressure to positive pressure, obviously the pressure gradient in this region is positive. Okay, but if you manipulate the TOV equation and write this in this form with an average energy density, this is basically the mass contained within a radius divided the volume, a cube. This is what we call the average density. Then you see that this quantity at the region where P is 0, okay, so this quantity will be positive. This is also positive. Everything is positive, and the gradient is negative. Okay, but the structure, the qualitative structure of the pressure profile in the gravastar requires a positive pressure gradient that is not accomplished in terms of this equation of state, or this equation for an isotropic fluid. So this is one of the reasons, or the main reason, why in this paper the gravastar was criticized as requiring an anisotropic fluid. Okay, a fluid that has different radial and tangential pressures. Okay, because in that case, for anisotropic fluids, the TOV equation gets this additional element, and this can naturally now justify these transitions. Okay, this positive gradient and then the negative pressure gradient that we find in typical isotropic fluids. Okay, so gravastars have this peculiarity that they need an isotropic fluid to exist, this is not a big problem, actually. This is, in fact, is very natural because the alternatives to black holes, the regular black holes, many of the regular black holes that one finds in the literature, they have a de Sitter core inside, okay? That is basically the same mechanism as here, but with the horizons. The Gravastar is like a regular black hole, but without horizons, so it's a regular star. And regular black holes with this de Sitter core typically are generated by nonlinear theories of electrodynamics, okay? And this nonlinear electrodynamics can be reinterpreted as anisotropic fluids, okay? So all this picture makes sense, okay? So there is nothing special, simply that the Gravastar has this peculiarity. It needs an anisotropic fluid to be generated, okay? So the objects that we are going to discuss, the Platypus stars, can be built using regular isotropic fluids, regular perfect fluids, the usual ones, the same ones as we saw before. So we don't need this additional characteristic that Gravastars have, okay? So now let me go to discuss the construction of the Platypus star. This is what we want to do. So basically, I copied the slide that I used for the constant density solution, and now we are going to implement the idea of an internal vacuum. Okay, so if the Gravastar is motivated by vacuum energy, understanding vacuum energy as the energy of a cosmological constant and the negative pressure associated to the cosmological constant, now we are considering the crazy idea that vacuum could indeed be empty, okay? Zero energy density, absolutely vacuum, the intuitive notion of vacuum and not the quantum-inspired notion of vacuum, okay? So we are going to assume that vacuum means exactly that the energy density is zero, okay? So if you take the equations of Einstein's equations as before, the TOV equations, and simply set the density to zero, okay, you get an exact analytical solution, okay? And the details are described here, okay? The first thing is the mass function. The mass profile, if the density is zero, is just zero. In general, it should be a constant, but we impose that this constant is zero, okay? So when the mass is zero, because the density is zero, then the function A is simply 1, okay? So A is 1. And then the conservation equation, the pressure gradient, is simplified. So we get that PR satisfies this equation here. So it's quadratic in P squared. So it goes like P squared. So this equation is separable and can be integrated. We can use the same results as before, simply that this A will be 1, okay? This density will be 0, so we get here a logarithm, and we integrate, we find an expression for the exponential. So this constant must be chosen in some way. Yes. That we take this, we set this constant by considering that the pressure at the center must be finite with some pressure, the central pressure, and that phi must have some constant value. So we don't really specify that, okay? Okay, so this is what we get for the integrating this equation. We find this expression here, and then the pressure profile is written here, and as you can see, it is simple. It is extremely simple. So it is a function that decays quadratically from a maximum. So it's a monotonically decaying function with the radius. And so it's a smooth decay, so nothing special happens. So this is just an exact solution of Einstein's equations, okay, with a non-trivial pressure profile, despite the fact of having zero density. Okay, yeah. Okay, so this is one of the questions of the Platypus. So can something like that exist? Well, the animal, the platypus, exists, even though it has very weird properties, okay? Now, how do we accept that something with zero density, zero energy density, can have pressure? Well, first, because it is an exact solution of Einstein's equations. Okay, if it is a solution, we must explore that solution, okay, and check the implications that it must have. Second, because in the prototypical model of gravitational collapse, the Oppenheimer-Snyder model, Oppenheimer and Snyder consider a particular limit that was the case in which the pressure is zero and the energy density dominates. Okay, but nobody considered the opposite limit, in which the density is zero and the pressure dominates. So this is the situation we are physically motivating. Okay, a scenario in which, for some unknown reason, the energy density becomes very small. It is actually zero. So for this solution to be true, we really need to put it to zero, but accept that the pressure, some kind of pressure, is not zero. Okay, it's a limit, a valid limit of the equations that must be explored, and that has received very little attention in the literature. Okay, so this is the main motivation why we are exploring this. Okay, it may seem unreasonable, something crazy, something unusual, like a platypus. Okay, but the platypus is there; they exist. You can go to Australia and find platypus. Okay, I don't know if in nature we will be able to find this kind of stars, but at least as theoretical physicists, it is our duty to explore them. Okay, and this is what we are doing, acting responsibly. Okay, so so this is the line element that we find as this is an exact solution, and this is the form that it has. Okay, it is spatially flat, so the spatial section is Euclidean. The time component is non-trivial. It grows quadratically with the distance, but everything is finite. All curvature invariants are finite. Everything is well behaved. The pressure profile is well behaved. Decays with the distance. So it's peculiar, like a platypus, but it seems to be well behaved. There is nothing that prevents us from considering something like this. Of course, what we want to do now is not to work with this line element, is to use this object, this part, to build a star. This will be we have a pressure that is the central mechanism that can support an external layer of fluid, like in a gravastar. In a gravastar, you have an internal mechanism that has negative pressure to support an external layer, and then connect that layer of fluid to a Schwarzschild. So we are not inventing the wheel. We are just following the established path, simply that assuming that vacuum can be really vacuum, empty, zero density, and using the resulting pressure to, at some point, for instance here, attach a fluid. We want to attach a fluid. Of course, I introduced the constant density solution for some reason. We are going to put a fluid with constant density for simplicity, but this is not necessary. The constant fluid simply will facilitate obtaining analytical solutions, okay, which are useful for the theoretical discussion. And outside, we will put Schwarzschild. Okay, something essentially like a gravastar, okay, but replacing the internal mechanism. Instead of vacuum energy, quantum vacuum energy, that is the cosmological constant, we now put actual vacuum energy, which is empty. Okay, very good. So this is how we are going to make our platypus. Okay, and then the step one is to build the core. We already found the core. This is the line element inside up to some radius. We will assume that from the center to R0, we have this core. Then we will attach some fluid, constant density fluid. And at the surface, when the pressure goes to zero, so we have Schwarzschild. This is the plan, okay? So step one is accomplished. We have already found the line element, we have the function A and the pressure profile. Step 2 is to add the constant density fluid layer. Okay, so we go to the previous calculations and simply reconsider the matching constant. Okay, for in this case, because now this condition is imposed, this particular, I'm looking here. This is imposed on the surface of the star, like in the previous case. And then we find that all this is the same, all this is the same, except for the fact that we need to put here an additional constant, okay, because we don't really know how to match how to evaluate this constant. I mean, we need to be consistent when joining the different parts of the star. So we cannot set this constant that in the case pure GR with the constant density star, that constant was 0. Now we leave it free and will be established once we consider the conditions, the matching conditions at the core. Okay. So basically we can get to this expression, which is identical to the one we found before, because we are doing some assumption. Okay, and the assumption is the following: that when we attach the constant density layer, we assume that the density is constant, and then the mass function, okay, if you remember, the mass equation is this one, okay? So in the platypus region, in the core, density was 0. Now in the constant fluid, it is not 0. So the integral is this one plus a constant. So, and we must choose the value of that constant, okay? If we wanted that the function m were continuous, okay, from 0 inside to starting at 0 at the junction between the core and the fluid, then this constant here should be minus k squared 6 rho 0 r 0 cube. Okay, this would guarantee that the mass function is continuous, but the price to pay would be that this equation here, this one, could not be solved in an analytical way. Okay, one would find hypergeometric functions and everything is complicated. So for theoretical clarity, okay, it is preferable to set C equal to 0 because it simplifies the analytical treatment of this equation. And well, if you want to do it numerically, there is no problem. Okay, you can do it. But we prefer to set C equal to 0 because it gives us more analytical freedom. This physically requires putting a thin shell of matter with a given matter amount in this junction surface, but this is not a problem. Actually, all gravastars stars at the junctions need thin shells. Okay, besides having the anisotropic fluid, you must impose some thin shells in the junction surfaces. So the fact that we are adding here a thin shell at this junction is nothing new. Okay, it's something acceptable, as in the gravastar model. Okay, and then this allows us to obtain this expression for the function A times phi, and then the pressure profile in the fluid region is given by this. Formally, this is the same expression as before for the constant density fluid, okay? But the main difference is that the central pressure now is not evaluated at R equal to 0. The critical point, where this quantity, this pressure would be infinity is when this denominator has a 0. But this 0 now is evaluated at the surface of the core, not at the center, not here. Okay, it's at the surface. So this makes a difference. So when you evaluate this quantity to be equal to 0, so in the constant density star, we found the Bogdan limit. Okay, in our case, if we do the math, this expression now becomes this one. Okay, right? Note that we have a a new element here, that is the ratio between the core radius and the star's radius. So if we make the fluid region smaller and smaller, so we turn it into a thin shell, basically. So when R0 goes to the stellar radius, then that ratio would be 1. And in that limit, the compactness of this platypus star tends to 1/2. It's like a Schwarzschild black hole. So this kind of star can be much more compact than a usual constant density star. Okay, and in fact, it reaches the compactness of a Schwarzschild black hole. So in principle, this looks like a very promising black hole mimicker. Okay, because at least many astrophysical phenomenological aspects will be identical. Okay. Okay, so one thing that we, just for technical completeness, this constant here can be set just to give continuity to the density, to the pressure profile, okay? The pressure in the internal region, the one that decays like this, and this other pressure profile will give continuity at the junction of the core with the fluid, and that fixes the constant ρ0. Okay, that initially the density of the fluid was free, but now continuity of the pressure profile is fixing this constant density. Okay, so it is no longer free. It is just simply given by this. Okay, this is under control. Okay, so this part is like that. So we have been able to connect the internal vacuum core with a fluid, constant density fluid, and obviously the constant density fluid is connected to a Schwarzschild smoothly, simply by choosing these constants. Okay, you can check that the pressure profile at the surface of the star is 0. Okay, so this is really transitioning smoothly to the external Schwarzschild region. So yeah, we have some good news that we have accomplished the making of this platypus star, taking pieces, to take a Schwarzschild from here, the constant density fluid from here, the weird vacuum solution from the other side, and you can connect all of them smoothly together to build a stellar model which can reproduce the compactness of a black hole, okay, of a Schwarzschild black hole. Okay, so this is the summary of the formulas. Okay, probably there is nothing interesting, simply the physics. So this is the external region, which is a Schwarzschild. This is the internal constant density star, and this is the core. Okay, note the domains of each region. Okay, and to get this constant, this difference of constant, the value of phi at the center and at the surface is simply governed by this demanding continuity of the GTT function, okay, at the junction between the core and the fluid. Okay, so the pressure profile is smooth, everything goes well, and that's it. And now, of course, now that we have the object, we want to explore its phenomenology, okay? And well, as you can imagine, well, since I don't have much time, I will skip many words here. We'll just show you the ray tracing of Schwarzschild. Okay, this is taken from the paper by Grala, Wood, and the other guy that I always forget. Sorry if you know him. My apologies. And so, since the platypus star reproduces Schwarzschild from outside in the constant density fluid region, if we make that layer very thin, so that R0 is equal to the surface of the star, basically, so we can make the core as compact as a black hole. So essentially, the geodesics, the light rays, the ray tracing will be identical to what we have here everywhere except beyond the black hole region, 2M. 2M is here. Okay, this is the Schwarzschild radius. So any geodesic will be identical. Any geodesic in the Platypus spacetime will be identical to the geodesics that you see here for the Schwarzschild black hole up to when they reach this surface. That is the core of the Platypus. Beyond that is what is new. Okay, and this is what we have to explore. Okay, so the curious thing is that, well, doing the typical analysis with conserved energy and angular momentum, we get this expression for the Platypus. It cannot be written as an effective potential, so don't expect the typical behavior with when you have an effective potential. It's something different. Okay, so what really matters in the equation for the propagation of geodesics is this denominator. Okay, it should be, we have a square root, okay, and the argument of that square root must be positive. Given the structure that it has, okay, it is easy to see that, well, it can be written like this. We're in the Platypus region, okay, so A is 1, and exponential of 2 phi is this quantity. This is a constant. And then this is like a difference of squares, and it can be rewritten in this form. And this will always be positive, and this is the one that can be negative, okay? So we need to look at this with more detail. And expanding, writing this B tilde of R. This B tilde is because it's just this product, okay? I don't know if this should be defined somewhere. Yeah, it's defined here. B tilde of R is the impact parameter of the geodesic we are studying, multiplied by this constant and by this function. So what we have here, okay, is this thing. And if you look at this is a quadratic equation, algebraic quadratic equation. So you find two roots, okay? And in such a way, the form of the roots is given here. So we will look at it in a while. But the point is that this quantity can be written in this way, okay? So this is only positive if the light ray, if the radius is contained between R plus and R minus. Okay, what this means is that light rays in this region, the Platypus region in the core, can propagate only between two in a region that is bounded by R minus and R plus. R minus is close to 0, is very small, and R plus is larger. Okay, but photons are oscillating between these two regions. Okay, so this is quite unusual and very uncommon, because this is like having photons trapped in some region, okay, which is the Platypus region, this region with peculiar properties because it has vanishing energy density. So photons can be trapped between these two for a given impact parameter. That photon is oscillating in spiraling, actually, it's in spiraling and out spiraling between these two radii. Okay, so we were a bit quite surprised by this property because this is like a mechanism to trap photons, don't let photons go out, but without having horizons. Okay, this is like a new mechanism to trap horizons. So, and this is like a good property for something that could mimic a black hole. Okay, so we need to look at this in more detail. Okay, so in summary, so inside the Platypus region, we find bounded photon orbits. Okay, that could be trapped, and then we look at this region, this bounded region in more detail. So this is the curve that represents the R plus solution in blue. In red, we have the R minus. As I said, R minus is always very small, with the maximum being here. Okay, the two solutions coincide in this maximum value in these units. RC is a constant that is related to the central pressure, PC divided 4. Okay, but just to simplify the expression for the pressure, we wrote it in that way with RC. instead of writing the pressure. Okay, so if you get a photon with a given impact parameter, it can only exist between these two regions, between these two radii. Okay, so it will be oscillating between these two regions. And impact parameters start here from 0 and grow in this direction. Okay, so this means that that the behavior of photons in this region is going to be crucially dependent on the relation between the size of the region, R0, the size of the core, and the value of R plus. Okay, because for instance, if R0, if we write R0 like this, imagine that the core of the star has this size, okay, then any impact parameter in this domain, when it gets the photons, will always reach this region because it's approximately R0, okay? Remember that we were assuming this going to 1, okay? The surface of the star is like this line, okay? So photons, since gravity in the Schwarzschild and in the fluid is attractive, so photons will fall towards this surface that is somehow replacing the event horizon of the Schwarzschild black hole. And then when they get here, if the impact parameter is in this domain, photons are not allowed to be here. So they cannot get in. So they will bounce, they will be reflected, okay? So there is a range of impact parameters that will not be able to get into the central core, okay? But if you decrease the impact parameter, then this region is allowed to enter because R plus is bigger than the size of the core. So the geodesic equation in this region for this range of impact parameters is not complex, it is real, and then photons can naturally propagate from outside to the interior, okay? They will propagate inwards, will reach R minus, and then will spiral outwards towards the R plus, but when they cross R0, then they are in the fluid and they will escape, okay? So this is basically one of the funny things that photons will do here, okay? Unless the size of the core is smaller than this extremum value, then we will always find this interval of prohibited impact parameters that will be reflected, okay? So as I said, this is work in progress. We don't yet have the intensity profiles and the geodesics ray tracing. We are working on it, but this is basically the phenomenology that we will find, okay? Depending on the structure of the size of this of the core, some range of impact parameters will not be able to enter the core and then come out. So they will be reflected. And this should have peculiar observational effects, okay? And with this is summarized in this diagram. It's basically the same as I told you. Just to conclude, this is basically what I wanted to say. We have found a new type of star that is supported by pressure, but has a vanishing energy density, and we call them platypus star. Unlike grava stars, platypus stars can be described by isotropic fluids. Okay, we don't need that. That's I think it's something in favor of platypus stars. And the compactness of these objects, of these platypus stars, is given by this expression, and in the thin shell limit, they become as compact as a Schwarzschild black hole, which in my view is something very interesting. And then the internal geometry is such, of this object is such that some photon bands might not be allowed to go through the core boundary, okay? So this will have, for sure, observable effects in the intensity profiles, okay, and the geodesic, the motion of geodesics. And as a spoiler, and to relax a little bit the tension, the condition of zero density is necessary in pure general relativity, but you can find platypus stars with non-zero energy density in other gravity theories. Okay, we have some analytical models that do that. So if you were too concerned with this unexplained phase transition or whatever, we can relax that. Okay, and that's all. Thank you.
Thank you very much, Gonzalo. I see some clapping.
Yeah, I see that.
I hear some echoes. Anyway, so now I think we have time for some questions. And I can start with the question. I mean, first of all, I thought it was very interesting. We always think these exploratory models with different properties are very insightful in the sense of understanding how things can be different from what we normally know. And it's good to get out of the paradigm.
Yeah. Mm-hmm.
And observations, setups, there's always a few key questions that you have to be well aware of, I'm sure. And the first one, of course, because how such an object form and its mechanical properties. Although I don't think it's fair to say that you should have explored this, not at all. You're speaking. Perhaps you have already some thoughts about it. And the question is if you could share those with us.
So let me see if I got right your question, because there were some oscillations in the intensity of the sound. You are wondering about the dynamical formation of these things?
One thing, and the other thing, of course, this type of very compact stars could, have different abilities, which is related to the formation issue. So if you a bit about that, and what are your...
Yeah, at this moment, we only have this model, okay? We don't have a dynamical formation. We don't understand the possible stability, but in my defense, I will say that gravastars were first proposed, I think, in 2002, 23 years ago. And the first model of dynamical formation, I think, will be discussed tomorrow here, okay? It's not trivial to build dynamical models to generate these objects. And regarding stability, probably they will not be stable, okay? At least in pure general relativity, because this solution is built on the assumption that the energy density is exactly zero. If you change that, then things change completely. So even if a photon enters in this region, it will carry an energy density that is going to spoil. Even if it is a perturbation, it will have dramatic effects in the structure of this specific solution. But I think that in this case, we should not pay too much attention to the concrete details of the model. I think the main lesson is the phenomenology that it can offer, okay, and the mechanisms to generate that phenomenology, okay. So probably the way.
Thank you very much, Gonzalo. I agree with what you're saying. As I said, I think it's very insightful to look at these models. Okay. So then I will go through the part. Are there any questions? It's difficult for me to manage the thoughts for you, so I can just approach the microphone and ask a question if there is one. No questions?
Okay.
Okay.
No problem. So I have to teach in 10 minutes.
There was a lot of food for thought, and people are still to digest, but certainly there will be a discussion about this model. So, given the participants, I would just like to thank Gonzalo again for very interesting talk on the exploratory model. You'll be hearing more about it, I'm sure. And well, hope to see you soon, Gonzalo. Do the best, and thank you again for your time.
Thank you so much. Thank you so much.
Okay.
Well, enjoy the rest of the meeting.
Please, thank you so much, Gonzalo. Take care. Let's use.
Thank you. I have to leave now. Okay, I have to.
Okay. Okay.
Bye bye.
Thank you. And so now I'll pass the word to the auditorium. The next speaker is going to be Roldo, I believe, and I will myself go to the auditorium. So see you in a bit.